Right, here's another example of a single reactant type problem. We're trying to find the order, and we're given the time in minutes, and then we've got the concentration of N2O. As we see, as the time increases, the concentration of N2O decreases, and that's logical because it is reacting. So the next thing we're going to do is we're going to figure out what the order of the reaction is. And the way we're going to do that is we're going to find the natural log of each of these values and the 1 over N2O of each of those values. And the way we'll do that is we'll put the natural log into our calculator. We'll find natural log of this, we'll find a natural log of this, natural log of this, natural log of this, and those are the values we come out with there. Then we go 1 over this, 1 over this, 1 over this, 1 over this, and that gives us the values we've got over here. The reason we're using natural logs and inverses is because if we go to the integrated rate law table, you can see that the values of y that we're going to be looking at will be the value of concentration itself, then the natural log of concentration, and the 1 over the concentration. Remember, these are all lines, straight lines in the form of y equals mx plus b. So those will be the y values that we're looking for. The x value in each case will be time. So going back to our initial table here, we're going to be graphing the time versus N2O, the time versus log of N2O, and then the time versus 1 over N2O. And we're going to see which of those is going to pop out to be a straight line. So we do time versus N2O, we get a curve. We do time versus log of N2O, we get a straight line, that's nice. And then we get a curve for time versus 1 over N2O. So the one that actually comes out to a straight line is time versus log of N2O, which tells us that the reaction must be first order. Now the logic behind that, again, is we go back to the table with the integrated rate laws, and what we find is that since this one is the one that gives a straight line, log of A versus time, then we know that that one's going to be the first order reaction. Alright, so we know our reaction is first order. The other way that we can find this is by finding the slopes of a couple of points in the line rather than doing the graphs. And what we could do is for the N2O, for example, we would maybe find the slope of the points between these two, and then the first and the fourth, and those are going to come out to be different values. Whereas if we take the natural log and we take the value of the slope between here, which would be negative 2.48 minus 2.69 over 15 minus 30, that would give us a value of negative 0.0140 for the slope. And then if we took the value of the slope between this and this one, that's negative 2.48 minus 3.95, and divide that by 15 minus 120, we're going to come out with a pretty close value. It might not be exactly 0.0140, but it's going to be close. Certainly close enough to say that this would definitely be the straight line. So we know that if we're going to get the same slopes for different sets of points, then we're looking at a straight line. So that's a way of doing it so we don't have to do the graphs. So we've got the slope of the line, it's negative 0.0140. This is going to enable us to also pick up K, which is the rate constant for the reaction. Now if we go back to the initial integrated rate law problems, we can see that we've got y equals mx plus b, and in each instance the slope will be negative k, or k in this instance. And the sign of k is always going to be positive. The slope can be negative, but the sign of k will always be positive. In this instance, the value of slope is negative 0.0140, which we got from up here. And that means that if m is negative 0.0140, then what's going to happen is the k will be the negative of that slope, which will end up being a positive value. So even though the slope is negative, the k will end up being positive, as it will always end up being positive, and it comes out to 0.0140, and its minutes to the minus 1 is the unit. The way we get the units on this one is that we look over here, we see log of N2O is going to be on the y-axis. That's not going to have a unit because it's a natural log. And the time has a minutes unit, and that's on the x-axis. And that's okay. That means that when we take the slope of this, it's going to be change in y over change in x. There's no unit here on the y-axis, but there is a unit here on the x-axis. So it's going to be 1 over minutes. So minutes to the minus 1 will be the units on the slope in this case. So after we've gotten the slope for that, we can go ahead and calculate the half-life. Now the half-life we're going to get by plugging it into the appropriate equation. Since it's a first order reaction, we're going to use the first order equation. I got 0.693 here. 0.693 is the same as log 2. That's the other way of expressing this, log 2 over k. So I go back over here and I plug in my values, and it's going to be 0.693 over the value of k, which is 0.0140 minutes to the minus 1. And you'll see we'll get the right unit here because it'll be 0.693 over minutes to the minus 1, which will give us minutes here. So the half-life is going to come out to be 49.5 minutes in this instance.